Oh, hello everyone. I thought I'll create a video where we walk you through the lubrication approximation. I wanted to do this because we just started this off in class, and I wanted to finish this in the video today. So what is the lubrication approximation? It is basically you start off with the Navier-Stokes, and the idea is based on some simplifications, you can really simplify the based on some assumptions. You can really simplify the Navier-Stokes to the following simple relationship, right? Where there are two velocities, both Vx and Vy, and Vy is not necessarily zero, but Vy is going to be much smaller than Vx, and we will show you how that is also true. Okay, so this is what is known as the lubrication approximation, and even in the lubrication approximation, now Vx is a function of both x and s is a function of y, and the pressure gradient dou p dou x is just going to be a function of x, right? So there are these number of simplifications. Now the question is, what are the assumptions that you need to simplify the Navier-Stokes to get to this particular equation that is shown here, right? So how do you do that? So basically, I mean, look, what is given here is this is steady state. Okay, so this is steady state. So basically, you neglect the time derivatives. So this is the x Navier-Stokes, and this is the y Navier-Stokes. So basically, all of this should just reduce to this. Okay. So when is this going to happen, right? So that is the question. So if you want to reduce the x and y to just this one equation, when does this happen? And what is the condition that is required, right? And what are the constraints? Actually, we can show that, I mean, there are 4 conditions, but these 4 conditions that are shown here are going to arise when two constraints are valid. The 2 constraints are, what is the Ly over Lx is much less than 1. And this is what is known as a geometric condition. And the other one is what is known as the dynamic condition, where Reynolds number times Ly over Lx is much less than 1. So, which is what is written here. So basically, if these 2 constraints are valid, then all these 4 conditions are going to hold good. I mean, what does this mean, right? I mean, look, so basically the first condition is my pressure is just a function of x. It is not dependent on y. So what this is saying is basically the terms in the y Navier-Stokes, the y Navier-Stokes is much less than the x Navier-Stokes. Okay, so all these terms, so this term is much less than this term, right? So basically what you're saying is dou p over dou y is negligible, and p is just a function of x. Okay, so basically the y Navier-Stokes does not come into play, right? I mean, because these terms are negligible compared to the x Navier-Stokes. Now let's look at the x Navier-Stokes, right? So the only terms that come into play now after the simplification are this and this. So basically what you're saying is the rest of the terms, say call this, this, and this, say call this 1, 2, 3. All 1, 2, and 3 are much less than, call this 4, are much less than 4, right? So basically, if this is true, if 1, 2, and 3 are much less than 4, under what, when is that valid, right? When can you say term 1 is much less than term 4, right? And those are the 4 conditions, right? Look at that. So basically, dou squared Vx should be much less than dou squared Vx over dou y squared. So 3 is much less than 4, right? When is this valid? Ask yourself that question. So look at this. This is term 1. Term 1 is much less than term 4. Okay. So basically, you neglect this. Again, term 2 is much less than term 4. Okay. So you can neglect this, right? And you can neglect this as well. So under what, and when are these terms much less than term 4, right? All of this is going to hold good when these constraints are valid, when the geometric constraint and the dynamic constraint. All this is saying is Ly, which is a characteristic length scale in the y direction, is much less than Lx, the characteristic length in the x direction. And this is what is known as the dynamic condition. And we will get to that in a second, right? When these two constraints are valid, all these 4 conditions will hold good, right? So how is that? So let's look at that in a little bit more detail. The first step is always the continuity. So dou Vx del dot V is 0 for an incompressible flow, right? Del dot V is 0. So that is the classic continuity, right? So del dot V is 0. So dou Vx over dou x plus dou Vy over dou y is 0. So Lx and Ly are the length scales in the x and y direction. U and V are the respective scales for Vx and Vy. So if dou Vx over dou x plus dou Vy over dou y is 0, so basically U over Lx is the same as V over Ly, right? V has V is Vy is V, Vx is U, right? So characteristic length scale in the x direction is Lx, right? And the characteristic length scale in the y direction is Ly, right? So U over Lx is the same as V over Ly. So look at this, right? So I'm just rearranging. So if you rearrange, what do you get? You get V over U is almost the same as Ly over Lx. Okay, so a magnitude of the velocity in the y direction is V, and the magnitude of the velocity in the x direction is U. So V over U is Ly over Lx. Now, again, if you choose a channel in which a characteristic dimension in the y direction, if Ly over Lx is much less than 1, then V over U is also much less than 1, correct? So which means Vy is much less than Vx. So there is a velocity in the y direction, but its magnitude is much less than Vx. So this is our geometric constraint. Remember that? Okay. So if Ly is much less than Lx, you get V over U is much less than 1. Okay. So now let's go on to the Navier-Stokes, right? Which is what we need to get at, right? And we need to simplify these terms. Again, the only terms here is the x Navier-Stokes. And the only term that, that finally should hold good are these two, okay? So the rest of the terms are going to be negligible compared to these. So how do you do that? But first, before I do that, what I've done here is just an order of magnitude estimate. So look at that. Vx is U. Dou Vx over dou x is what? U over Lx. Vx has magnitude U, and it occurs over a length Lx. Same thing, Vy is V, and dou Vx over dou y is U divided by Ly, okay? Same thing, what is dou squared Vx over dou x squared? Is nothing but Vx is U, and it divided by Lx squared. So dou squared Vx over dou y squared is nothing but U divided by Ly squared. So these are all the different terms, okay? So say now this is the y Navier-Stokes, right? So again, now you do an order of magnitude estimate. Vx is U. Dou Vy over dou x is nothing but V divided by Lx, right? And now, okay, so again, Vy, dou Vy over dou y. Vy is V. Dou Vy over dou y is nothing but V divided by Ly. Same thing, dou squared Vy by dou x squared is V over Lx squared. And this term is V divided by Ly squared. So before you look at the x Navier-Stokes, it's easy to show that the y magnitude of the terms in the y Navier-Stokes is much smaller than those in the x, right? Say, for example, let's take these two terms. That's 1 and that's 2, right? So look at this. u squared over Lx, this is the term in the x Navier-Stokes. uv over Lx is the term in the y Navier-Stokes. So look at that, u squared over Lx, and I'm comparing it to uv over Lx, right? This is a term in the x Navier-Stokes, and this is the term in the y Navier-Stokes. So which term dominates, right? So look at that. So say let's do the y Navier-Stokes divided by the x Navier-Stokes. What do I get? So I have uv divided by Lx divided by Lx divided by u squared. I get v over u. Now I know that v over u is much less than 1, right? Which I've just showed you, because the velocity in the y direction is negligible compared to the velocity in the x direction. Why? Because my Ly over Lx is much less than 1. So which means that this term in the y Navier-Stokes, uv over Lx is much smaller than u squared over Lx. I mean, you can similarly show that for other terms as well, right? For example, look at this, vu over Ly. This is v squared over Ly. Obviously, I mean, this term is going to be negligible compared to this term, right? So basically, you can show that for any term in the y Navier-Stokes. I mean, look at this, right? v over Lx squared, u over Lx squared, v is much less than u. So this term dominates much higher than this term, right? Similarly, so you can show that the terms in the y Navier-Stokes are much smaller compared to the terms in the x Navier-Stokes. So which means that my dou p over dou y is negligible compared to dou p over dou x. And all you needed here was to show that, you could show that the terms in the y Navier-Stokes is small compared to the x Navier-Stokes just with one condition, Ly over Lx is much less than 1, the geometric constraint. Okay, so I mean, it also makes sense, right? I mean, if you have, say, very narrow channels, I mean, the pressure variation, all this is saying is the pressure variation in the y direction is negligible compared to the pressure variation in the x direction. So the geometric constraint, when I say Ly over Lx is much less than 1, it takes care of showing that the terms in the y Navier-Stokes are much smaller compared to the terms in the x Navier-Stokes. Okay, now let's go on to the x Navier-Stokes. Okay, so again, let me let's write the terms in the x Navier-Stokes again. Okay, so let's do that. So just bear with me. I mean, let me write this down here. So x Navier-Stokes reads rho times Vx, dou Vx over dou x plus Vy, dou Vx over dou y is equal to minus dou p over dou x plus mu times dou squared Vx over dou x squared plus dou squared Vx over dou y squared. So let's do an order of magnitude estimate again. I mean, let's just work through this. Vx is u. Dou Vx over dou x is nothing but u over Lx. Vy is v. Dou Vx over dou y is nothing but u over Ly is equal to minus dou p over dou x plus mu times dou squared Vx over dou x squared is u divided by Lx squared. Oh, sorry. Plus dou squared Vx over dou y squared is u divided by Ly squared. And again, the only terms that are going to remain are these two, right? So, okay, so let's look at this first two terms, right? I want to show that. So first let's look at this term and compare it to this term. Okay, Dou squared Vx over dou x squared, u over Lx squared. Dou squared Vx over dou y squared is u over Ly squared. I'm just taking the ratio of those two terms here, right? U over Lx squared divided by u over Ly squared. What do you get? Ly over Lx whole square, right? And I know that my geometric constraint is Ly over Lx is much less than 1. So boom, this term is negligible compared to this term. Voila, again, same thing, geometric constraint. So, so let's look now. Let's come to these two terms, okay? Vx, dou Vx over dou x, and it should be rho times Vx, dou Vx over dou x, and I want to compare that to dou mu times dou squared Vx over dou y squared, okay? So how do I do that? I mean, let's take the ratio of those two terms. So that is, let's take the ratio of those two terms. So basically I need this and I need these, okay? That is rho times u squared divided by Lx divided by mu u divided by Ly squared, okay? So, so what do I get? Let's see. I'll cancel that. So I have rho u. I'm going to take Ly over mu. Rho u. I'm going to take 1 Ly over mu times Ly over Lx. So this is Reynolds number times Ly over Lx. And that is my dynamic constraint. My dynamic constraint is Reynolds number times Ly over Lx is much less than 1. Voila. If my geometric constraint holds good, then all I'm saying is this term is negligible compared to this term. Okay. So now, how about this term, right? Vy dou Vx over dou y. Let's do the second initial term, rho times Vy dou Vx over dou y. And I'm going to compare that to mu times dou squared Vx over dou y squared. This term is rho V u, rho V u divided by Ly. And I need to compare that to mu times u divided by Ly squared. Let's divide the two. I'm going to get rho V u divided by Ly times 1 divided by mu u Ly squared. Okay. So Ly u I have rho V Ly over mu hold on, what's going on? Rho V u over Ly mu times u divided by Ly squared. Okay, so there is something going on. So this is just the Reynolds number, right? Rho, oh, sorry. Oh, okay. Thank God. Okay, so rho V Ly over mu. So sorry, that makes sense. Okay, hold on for just a second. So that is nothing but rho u Ly over mu times V over u. So this is Reynolds number. V over u is nothing but Ly over Lx. So much less than 1. It again comes back to the geometric constraint, right? So this is a second term in the Navier-Stokes, right? Look at that. Rho V u over Ly. And I'm going to compare that to mu u over Ly squared, right? So basically, again, if the geometric constraint holds good, then I can neglect the initial terms as well compared to the viscous terms. So again, right, coming back to the Navier-Stokes. So basically, the Navier-Stokes simplifies, and it comes down to the simplified lubrication approximation when two constraints are valid. The geometric constraint Ly over Lx, which is much less than 1, and the dynamic constraint Reynolds number times Ly over Lx is much less than 1. When these two constraints hold good, the four conditions are valid, and you can simplify the Navier-Stokes to the lubrication approximation. Please go through the book, and the book does an excellent job in explaining these things. Okay.